Welcome to our discussion on equations. I'm going to burn through some slides really quick that go through terminology, vocabulary. So if you actually don't know some of this vocabulary, just pause and read it. I don't want to waste everybody's time talking about what solutions are and what it means to, be a contradiction or blah, blah, blah. So instead, we're just going to move on to linear equations. Again, I'm not going to spend a lot of time. You can pause and read these. You all know what you can and can't do. The goal is to isolate one variable on one side of the equation. Don't always think it's x and don't always think it has to be on the left. That's one of the biggest mistakes that grade school teachers teach is they seem to make all of their students solve all of their equations for x, and then they also make sure that it's always x equals 5 instead of 5 equals x. So you get in this bad habit of thinking you always have to leave your variable on the left, and you don't. Like for instance with e, the easiest thing to do is just add x to both sides, and you see that x equals 15, right? So you don't have to keep them on the left. I'm also going to burn through most of these solutions quickly because I think you all know that all we have to do is subtract 15, add 36, divide by 3, multiply by 5, move the x over, right? So it's really easy. We don't need to talk about what are the names of those steps, that's the subtraction property or the addition property or any of that junk. Okay, let's remind ourselves that 15 equals x, the same thing as x equals 15. Like I said, you can have x on either side of the property. And in addition to that, for a specific type of problem, we can use a very specific technique to solve it. And that's if we have a repeating decimal and we want to turn that into a fraction. The technique to remember when trying to turn a repeating decimal, right, 7 repeating, into a fraction is to multiply both sides of your initial equation, right? You always let n equal just the initial number that you have, the initial decimal. Then you multiply both sides of the equation by enough tens, right, enough powers of 10 to get one full copy of the repetition over on the left-hand side of the decimal. And since this is repeating with just one decimal, right, 7, 7, 7, 7, 7, then you only need to multiply both sides by 10 because that'll give you one copy. So you see we start with 0.7 repeating, multiply by 10, and we get 7.7 repeating. And then now what you do is you take this second number and subtract the first one from it, right? Because they're equal, I can subtract on the left-hand side the n and get 9n, and on the right-hand side I can just subtract the 0.77, and this 0.7 repeating cancels this 0.7 repeating, and you're left with just 7. Then of course you divide both sides by 9 and you get 7/9. Now this only works because of infinity. You might be thinking, well, these 7s went on forever, and when I multiply by 10, they basically move over by 1. And so now don't I have 1 less 7? So these 7s should be 1 less than those? No, because there's no such thing as infinity minus 1. Infinity minus 1 is still infinity. If these two lists of 7s go on forever, then they're exactly the same size. That's the kind of the magic of infinity. So our second example was 0.123, but nothing repeated. There wasn't a bar over it. So you just simply rewrite this in terms of its decimal. This is the tens, hundreds, thousands place. So it's 123 over 1,000. You can also remember that there's 3 decimals, so you need 3 zeros on the end of your 1. And that's your answer for that. However, if you have this one, where 1, 2, 3 repeats, right? 1, 2, 3, then 1, 2, 3, and then 1, 2, 3 again. Then now, in order to get one full copy of the repetition to the left, we have to multiply by 1,000 instead of 10, right? Because again, 3 decimals, 3 zeros. And so now we have 1, 2, 3, 123 repeating. If you take this and subtract this from it, you're left with 999 of them. The decimals go away and you just have 123. And then you divide both sides by that and you get 123 over 999. You then, of course, have to reduce it because it can reduce. And your answer is 41 over 333. So the hardest part really is reducing fractions. Most calculators will reduce fractions for you, but even if they don't, you should be able to reduce them pretty easily by hand. Okay. This last example can feel a little tricky. Some books actually do it, and some instructors do it a different way. They'll start with the original, right, 7.5, and then it repeats 64, 64, 64. And what they'll do is they'll just multiply this by 1,000, right? 1, 2, 3, to get the decimal after one repetition, and then go from there. Some will multiply it by 2. There's all sorts of different ways, and it all comes out in the wash at the end. The way I like to do it is I like to always reset the question so that they're always the same, right? We noticed in our previous two examples that the repetition started directly to the right of the decimal. We had 0.7777, we had 0.123123, and it doesn't matter what number is to the left of the decimal as long as it starts with the repeating sequence. Well, this one doesn't do that. It's 7.5 and then 646464. So what I do is I multiply both sides by 10 to begin with. And that gives me 10n equals 75.646464, blah, 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 right? So now it repeats from the decimal on. Then all I have to do is take this new equation and, like I did with all the other examples, multiply by the appropriate power of 10 to get one copy of the sequence to the left of the decimal. And since it's a 6-4, right, it's a 2, I can multiply both sides by 100, and that gives me 1000n, and then 7564.64646464. And now this mirrors all the other examples, right? It makes the recipes more similar. It makes it easier for my brain to understand how to do all of these because I now have kind of this skeleton idea that fits all of them. No matter what they give me, I just reset it so that it matches the pattern of a bunch of numbers to the left of the decimal, doesn't care if it's just a 0 or anything else, and then the decimal is where the repetition starts. So whatever the sequence is, that repeating sequence always starts right at the decimal. And then the rules are always the same. Then you multiply both sides of that equation by a power of 10 that matches the length of the repetition, in this case, 2 of them, so 100. Then you subtract the two differences and reduce the fraction if necessary. So you do this subtraction. 1,000 minus 10 gives you 9,090. Well, that's a stupid mistake. Obviously, 1,010 minus 10, 1,000 minus 10 gives you 990. Sorry. And then 7564 minus 75 gives you 7489, and then the decimals go away. And to me, this is a lot cleaner than the way other books do it, where your result then has a decimal in it. Then you got to multiply top and bottom of your fraction by powers of 10 to get rid of those decimals. And it's just, I don't think it's as easy as doing this because now you're back to this thing at the bottom, which is exactly like all the others. So the last step is just divide both sides, right? So in this case, divide by 990. And then reduce if you can, but it doesn't reduce. And this is your final answer, right? So that's the way I would tackle them, guys. The last type of equation we want to look at in this video are quadratic equations. These are the most important equations. These are the most common equations. You will see these more often, really, than any other function other than maybe linear equations. Quadratics show up everywhere all the time in all sorts of subjects: physics, chemistry, business, finance, calc, they're all over the place. So you really want to become familiar with what a quadratic is, what it looks like, what are the properties of quadratics, what are the graphs of quadratics look like, how do you find the zeros of it, how do you find the minimum, the maximum, how do you find the vertex, how do you find the lines of symmetry. I mean, all those things you're going to want to know about quadratics, and different videos of mine will show you how to do all of them. But for now, we're just going to learn how to factor them and find zeros, right? So we always want to take our quadratic and set it equal to 0. And if it's in this form, right, because not all quadratics are in this form. What I mean is not all quadratics will have the bx part or the c part. And sometimes a will be, 1 or different numbers. But if it's in this particular form, then you can always use the quadratic formula to solve it. If the numbers a, b, and c are simplistic enough, you can always try factoring first. So for instance, given this equation, if you have to solve it, you got to get rid of grouping objects. You got to actually do the distribution, right? Then you see, oh, I've got a squared term and a linear term and a constant. I've got all the pieces that make up a quadratic. I know the only way to solve a quadratic is to put everything on one side, set equal to 0. So here it is. And now that I have this is really easy because x squared can only factor 2x and x. 36, I have to find factors of 36. So I can try 9 and 4, and that doesn't work, and 12 and 3, and that doesn't work. But 6 and 6, sure enough, gives me 12 in the middle. So I know it factors this way. And then if I was solving for the zeros of this factor, or this thing, I set each one of these equal to 0, and that means x minus 6 equals 0, so x equals 6. And then x minus 6 equals 0 gives you x equals 6 again. So the only solution is, now technically that solution has a multiplicity of 2. And multiplicity is important only later on when we're dealing with polynomial functions and we want to know how to graph them, and we want to know if a 0 means that it crosses through the axis or if it bounces back. And if you have a multiplicity of 2, i.e. any multiplicities of even numbers, then we know it hits and bounces back, whereas odd multiplicities, it crosses through. But again, that's a topic for a different video. Okay, here's the quadratic formula that I think most of you are probably well aware of. It's pretty popular, it's pretty common, you use it a lot. I suggest that whenever you have a quadratic and you're going to use the quadratic formula, the first thing you do is literally write a equals and put whatever it is, b equals whatever it is, and c equals whatever it is. Because if your original function has some minuses in there, you're going to tend to make mistakes. So for instance, if your original function, let's say, was 3x squared minus 5x plus 7. You have to remember that a equals 3, that's pretty easy, but b equals negative 5, right, because of this negative here. And then c equals 7. By taking half a second to writing these three things down, it'll keep you from making a mistake of forgetting to, now all of a sudden this is going to be positive because it's minus a minus 5, that type of thing. So my suggestion is to always write those numbers down before you start actually plugging it into the quadratic formula. Now, don't use the quadratic formula unless you have to. Please try to factor things first. It's a great skill to have. It's a necessary skill to have for a lot of subjects. So it's good to practice it as much as you can. And then when it doesn't factor easily, that's when you go back and use the quadratic formula. If you tried to factor this one, you'd know that it has to be 2x and x because that's the only way to get 2x squared. And it has to be 1 and 1 because that's the only way to get 1. And that would give you 2 and 1, right, when you do the 2x times the 1 and the x times the 1. And that would add to 3. So this thing doesn't factor with whole numbers. So we would have to use the quadratic formula, plug everything in, and sure enough, we get an answer with a radical in it. That's the other thing you have to worry about, guys, is you have to be able to reduce your radicals, right? Square root of 8 is 4 times 2. The 4 becomes a 2 on the outside, right? So this becomes 2 root 2. And then now you can reduce everything because everything's divisible by 2. You're basically factoring a 2 out and then canceling it with the bottom. 2 and 4 reduces to a 1 and a 2. So you're left with just what's inside the parentheses because the 1 just goes away. All over 2. And that's your most reduced version. This one, also, if you tried to factor it, the only factors of 13 are 13 and 1, and those aren't going to give you 6 in the middle. So you plug it into the formula, and look what happens. You get a negative 16 underneath the radical. Whenever you get a negative underneath the radical, there are no real solutions. Normally, you're only working with real numbers, so at this point, you would be done. If you were working with imaginary numbers, you'd have to realize that this, right, the negative 1, square root of negative 1 becomes an I on the outside, and then root 16 is 4. And if you were dealing with imaginary numbers, your answer would be 6 plus and minus 4i all over 2. And then, of course, everything here is divisible by 2, so it would be 3 plus and minus 2i, only if you were doing imaginary numbers. And most times you're not allowed to have imaginary roots. You would just say there are no zeros. All right, that's everything for this video.